So problem 23, you're given a buffered solution and you're asked to figure out what the pH would be after the addition, in this case, of HCl. But keep in mind, this could also be sodium hydroxide, in which case we're going to have to do things a little differently for that one, but I will show you where the differences would be if we were to use sodium hydroxide as we're going through the problem. So we're going to start off here with the initial moles. Let's get a pen here first. And we'll do the AH first. And to get that, we use the initial concentration of the AH portion of the buffer, which is 0.77 moles per litre. Multiply it by the volume we have of that buffer portion, and it's going to be 0.4319 litres, which is 431.9 millilitres converted into litres. And that comes out to be 0.334 moles. We do the same thing for A minus, and we use 0.730 moles per litre, the concentration of the A minus initially. Multiply that by the volume, which is the same as the previous one, 0.315 moles is the answer for A minus. This is initially. We also figure out the amount of H plus, or the moles of H plus being added. When we do add it, it's going to be 0.207 moles per litre multiplied by 0.00660 litres. That's 6.60 millilitres converted into litres, and that comes out to be 0.00137 moles. This will always be, this H plus here, or OH minus, will always be smaller than either of the moles of AH or A minus that we get at this point. The next thing we do is we figure out the reaction moles. Now this is the most important part of the problem, I think. So let's look at reaction moles. We'll put that up here. And we're going to look at AH first. And to get the reaction moles of AH, it's going to be the initial moles of AH plus the moles of H plus added, which is going to be 0.334 moles plus I'll just do it down here, plus 0.00137. So these were the figures that we got from here, this one, and this one. Now this comes out to be 0.335 moles. Now keep in mind that this is addition rules, so it goes by that number of decimal places. So 3 decimal places is the smallest, so that's what we go with, 3 decimal places, 3 decimal places. Then we look at the reaction of A minus, and that's going to equal the initial moles of A minus minus now the moles of H plus added, and that's going to be 0.315 minus the 0.00137, which comes out to be 0.314 moles. Again, 3 decimal places, 3 decimal places, that's 5 decimal places. So the answer comes out to 3 decimal places. And you can see what we've used here is this specific one for the A minus, and then this one for the moles of H plus again. So let me explain exactly why we're doing plus here and minus here, because that's really the most important part. So what I'm going to do is I'm going to draw a picture here of what's going on. So let's say we've got a buffer and we'll have A minus, AH, and AH in here. In this case I'm adding H plus to the buffer, and what's going to happen is that the H plus will react, well, certainly won't react with the AH, it will react with the A minus, and what will happen is it will turn any A minus into AH, and the net effect of that is that for every mole of H plus we add, we'll end up removing or minusing the moles of A minus, and you'll notice that also the moles of AH end up going up. So the A minus goes down, the AH goes up. So that's why you'll see the positive here or the plus here for moles of H plus adding to the moles of AH, because every mole of A minus that gets converted into AH will end up being reflected here with this plus sign. And with the minus, you'll see that we're losing A minus, so the minus is indicating that the moles of A minus will end up going down. But the moles of A minus go down by the number of moles of H plus that are being added into the solution. Now if we were adding OH minus, as you might have to, well, as you would have to do if you saw an OH minus problem, we'd start off with the same situation of A minus and AH initially being in the solution. But then what would happen is that the OH minus would end up reacting with the AH and creating A minus. So what would happen is that the A minuses end up going up and the AHs end up going down. So in that situation, what would happen is that this plus here that I'm pointing to would end up becoming minus in the case of AH, and this minus that I'm pointing to here will end up becoming plus in the case of A minus, because you can see the OH minus causes the production of A minus and the loss of AH from the solution. Alright, so what I'm going to do is, now that I've got those figures, I'm going to erase everything I have here, so I have the room to do the rest of the problem here. Okay, so we've got the reaction moles of AH, and I'll go ahead and rewrite those here. And this is what we just calculated, and it comes out to be 0.335 moles. And the reaction moles of A minus, again what we just calculated, 0.314 moles. The next step is to find the concentrations in the reaction of AH and A minus. Now the reaction AH is going to be the reaction moles of AH divided by the total volume, which has to be in liters. And that's going to be 0.335 moles divided by the total volume, which is 0.8704 liters. I'll explain how I get that in a second. And that equals 0.384 molar. We do the same thing for the A minus, and it's going to be the reaction moles of A minus divided by the total volume in liters, which comes out to be 0.314 moles divided by 0.8704 litres, which is going to be 0.360 molar. Alright, let me go through how you get this total volume here. The total volume is going to be 2 times the volume of each individual solution, because each of them have the same volume initially, and that's 431.9 milliliters. And we'll add into that the amount of HCl being added, and then convert that into liters, so times 1 liter over 1,000 mils, and that's how we're getting 0.8704 liters for the total volume of solution. So the 0.384 and the 0.360, that's going to be our volumes, or our concentrations of AH and A- respectively, after the reaction with H+. Once we do that, we go ahead and set up a table so that we can calculate the pH of solution. So now that we've got this, the reaction that's in play is this one, AH gives A- plus H+. Let me move that over a little bit. There we go. And the equilibrium molar down here. Now the initial concentrations are the ones that are listed here for each one. So we've got 0.384 over here. We'll have 0.360 over here for the A-, and initially we assume that the H+ is 0. Now after a time, what's going to happen is that some of the AH will end up dissociating, so it will end up going down in concentration. The A- and the the A- and the H+ end up going up in concentration. And the amount they go up is this amount I'm calling delta. Now the reasoning for this comes about from what's going on in the reaction. So let's say you've got just AH and A- floating around in the reaction mixture. The AH can then dissociate and become A- and H+. And you can see that the effect of that is that for every AH that breaks apart, you'll get an A- and an H+, which is why the AH goes down, but the A- ends up going up. And the A- goes up by the same amount as the H+ goes up, which is this delta here. So that should explain to you why we're doing this, and why this table is going to be the same regardless of whether we're adding acid or base, because at this point we have the same result. We just have a solution that contains AH and A-, and that's it. Alright, so we've gotten that far. Now we need to make an assumption. Because it's a buffer, buffers have a definition where they're actually a mixture of a weak acid and its conjugate base. So we automatically know that we can make this assumption. We can say assume weak acid base. And what that allows us to do is say 0.384 minus delta is approximately 0.384, and 0.360 plus delta is approximately 0.360, which allows us to simplify our next calculation. So what I'm going to do is, I've run out of room here, so I'm going to get rid of this, and I will rewrite the thing that we have here. So what we have at this point is this situation. where we had the reaction, I'll rewrite the reaction up here. AH gives A minus plus H plus over here. And it's going to be A minus times H plus over AH. We're given the Ka in the problem here as 6.79 times 10 to the negative 5. I'll rewrite this table here so you can see exactly where the values come from. Now remember, we already made the assumption about these guys here that these would equal the values that we have. And what we can do then is just take these values with the assumptions here. The A minus 0.360 and the AH, which is 0.384. Now we're going to solve for delta, and delta is actually going to be equal to, as you can see here, the concentration of H plus. And when we solve for that, which we'll do by multiplying 6.79 times 10 to the negative 5 times 0.384 and dividing by 0.360, we come out to 7.24 times 10 to the negative 5. Then we can find from that the pH by taking the negative log, and that comes out to be 4.140. And what we know is that the number of decimal places here in the log is going to equal the number of significant figures in the number that we start with. So we come out to 4.140 here as the answer for the pH.